Today's explanation is on finding the exact value of each trig function. If you look at the unit circle, when we find exact trig definitions, there's also a big chart that I gave you. We're going to find the tangent, which is y divided by x of 3 pi over 2. On your unit circle, this is 0, this is, let me pick a different color, this is pi over 2, this is pi, this is 3 pi over 2. And then your ordered pair at 3 pi over 2 is 0, negative 1. So your 0 is your x, the negative 1 is your y. That means if you do the tangent of that, y divided by x, it's going to be negative 1 divided by 0. Anything divided by 0 does not exist, so you write undefined. Let's look at now the cosecant at 5 pi over 4. If we're trying to figure out where 5 pi over 4 is, they already showed it to us, but you can check on your unit circle that it goes to about right here. The ordered pair at 5 pi over 4 is negative square root 2 over 2, comma, negative square root 2 over 2. You might have something slightly different with the square roots involved with this, but it should look about like this at 5 pi over 4. The cosecant is the flip of sine. But sine is your y value. So we're going to flip the y value to make 1 over the y value. Here, your y value is negative square root 2 over 2. So you're going to flip it. So it's going to be 2 over negative square root 2. And that's your cosecant. Let's look at the secant of 300. 300 is like right here. Oops. Let me redraw that line. 300's about right here. And the ordered pair on the table in the unit circle, the ordered pair is 1/2, comma, negative square root 3 over 2. So we have our x and our y. But the secant is the flipped of cosine. But we know cosine is the x, because if you recall, sine and cosine in an ordered pair, the cosine comes first, the sine comes second. The cosine's the x, the sine's the y. So if you flip the x, you come out to be the flip of 1/2, which is 2. So that's the secant at 300 degrees. You look at 300 degrees, and then that ordered pair looks like this from the unit circle. It's the flip of the x. Go and look at number 22. Graphing could be tricky. I'm going to go over this in a lot of detail with a lot of colors. So if you have colors, let's do it. The normal sine function graph looks like y equals sine theta or sine x. That I'm going to put in black. I'm going to make some dots for it. You should have a basic outline of what the sine graph looks like. So a sine curve starts at the origin, goes up to 1, goes back to 0 at 180 or pi, then to 270, and then back at 2 pi or 360, it returns back. And then usually you could change these to radians. But this is not the normal sine. There is some other numbers attached to it. We have a 3 in front, and then we also have a 2. Let's see what the 3 does. What the 3 does is it changes the amplitude. So instead of going 1 unit high, it's going to go up to 3. And also instead of going 1 unit down, it's going to go down to 3. So now the graph is going to look like this. All the other dots stay the same. And then lastly, let's see what the graph looks like if we have 3 sine, but then we go +2 at the end. That +2 represents the d-value, which moves the graph up or down. So basically, we're going to take all these points and go up 2. So from here, I'm going up 2. 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 And you're always going to have 5 critical points, 5 dots, whenever we graph these sine or cosine graphs. It's going to go up, connect it, and connect. The pink graph is final. That's the final answer. And you are done. Let's go on to the next one. We have tangent of theta over 2. Let's look what a normal y equals tangent graph looks like. Those have asymptotes at every pi over 2. That means there's barriers whenever you have a denominator of 2. Looks like that. And the basic shape is that it starts at the origin, goes up and back down, and then in between the 2 barriers, the 2 walls, it's going to go up, back down, kind of curvy. It's going to go up and back down, just like that. But let's talk about what the tan of 1 theta over 2 represents. The 1/2 is the b value. What the b does, the b changes period. If you remember, the period formula for tangent is pi over b. Excuse me. The period formula is pi over b, what I said before. Just checking. What a normal period is for a tangent is pi. It repeats every pi. But here, we have a different b value. The b is 1/2. So the period's going to change. We're going to plug in 1/2 in for b. Pi divided by 1/2. Let's do that on the side. I'm going to times it by the reciprocal. So I'm left with 2 pi. What that means is that the tangent's going to be expanded by 2 pi. Let's erase this graph so we can better see. Just remember that the asymptotes were still at every pi over 2. We're just going to double all of these. We're going to take all the asymptotes and double everything. Since we normally have a period of pi, we're going to change it to 2 pi. So we're just going to double everything that we see. So instead of an asymptote at pi over 2, we're going to double it to an asymptote at pi. And we're going to double the next one. So instead of an asymptote at 3 pi over 2, it's going to have an asymptote at 6 pi over 4, which is about 3 pi over 2. Sorry, it's 3 pi when we multiply 3 pi over 2 by 2. And then we still have the starting points here. And then in the middle, we have this going on here. So basically, we expanded it, almost zoomed in almost. When we change the period, we're zooming in or zooming out, making it repeat less or repeat more. Now, write down any questions you have for me to further explain this to you in class on tangent.